In this lecture, we are going to discuss about set reset flip-flop. And if you want to know why flip-flops are important and why we are using flip-flops in a combination logic circuit and what makes the difference, you can visit the video and the link is given in the description. But if you know the purpose of having a flip-flop, you can continue watching this video. And in this video, in this lecture, we are going to see about SR flip-flop or set reset flip-flop. And this is the simple diagram of a SR flip-flop or set reset flip-flop made using NAND gates. Right? You can write here, it is made using NAND gates. Right? So these are the four NAND gates. This is NAND gate 1, NAND gate 2, NAND gate 3 and NAND gate 4. Right? See, you can see this NAND gate 2 and 4, they are latched. That means the output of NAND gate 2 is given to the NAND gate 1, NAND gate 4, so like this, NAND gate 4 like this, and the output of NAND gate 4 is given to the input of NAND gate 2, right? In this way, NAND gate 2 and NAND gate 4 are latched, right? And in this, Qn will be the present state of the flip-flop, right? So present state, it may be anything, it can carry anything, right? It will be anything. So this will be the present state which is coming out of the NAND gate number 2, and from the NAND gate number 4 you can have this complement of the present state. Whatever is there in the present state, there will be a complement of this. If it is 0 0, it will be 1 1, right? And all we have to do during this operation of discussion here, we are going to find Qn plus 1. And what is Qn plus 1? If Qn is the present state, then the next state will be Qn plus 1, right? And if the present state is Qn, the PS, the present state is Qn, the complement is Qn bar, the next state is Qn plus 1, right? The complement of the next state will be Qn plus 1 bar, right? So all we have to do here is to find what is this Qn plus 1 is what, right? So that is what we are going to see for all the values of nothing but S and R. Let's see how we can do. And I have the truth table with me. I'll just paste it here, and this is the truth table, right? So we can fill this truth table like this. We can add values to this. So for all the values, I told you, for all the values, it refers to the values of what you call is SR, S and R. So initially S will be 0, R will be 0, and S will be 0, R will be 1, and S will be 1, R will be 0, and what if both are high values, right? As I told you earlier, you don't care about the present state of this flip-flop. You don't worry about the present state of flip-flop. So we put don't care, and don't care, right? You only worry about the next state. So it is Qn plus 1, right? You worry about the next state. So we are going to apply values for S and R here, right? And we are going to see how this thing works and how we can get values for Qn plus 1. So that is what we are going to see. Now we can go back to this diagram. So we have to add one more thing here to this diagram, which is nothing but the clock. Without the clock, this circuit will not work, right? There will be memory, right? You need a trigger, a signal to provoke the memory, right? So if I ask you what you were doing yesterday afternoon, right? Yesterday afternoon is the information I'm giving you, right? So that you are recalling what you were doing yesterday afternoon. What did you study yesterday afternoon? What assignment you were writing? What kind of book you are reading, right? And what kind of movie you are watching. So you need a provoke, right? So that provoke is nothing but your clock. Here you are applying a clock signal, right? The clock is always kept high, right? There is no low value for this clock. The clock is always kept high. If the clock is 0, the circuit will not work. So S is applied here and R is applied here. S stands for set and R stands for reset. Now let's see how this thing works. For this, you can take four cases. So this is case 1. Case 1 is nothing but for s equal to 0. Case 1, can put case 1 for s equal to 0 and or equal to 0, sorry, or equal to 0. So this is the first case from this truth table. Let's see what is happening here. For s equal to 0 or equal to 0, s equal to 0 and or equal to 0, right? So one input of this NAND gate 1 is 0. This 0 comes from the s and this 1 comes from where? It comes from the clock. So 0 dot 1. Since this is a NAND gate, there will be a whole bar, right? 1.0 is 0, so 0 bar is equal to 1, right? This one will be going as an input to the NAND gate 2, right? So this NAND gate 2 has two inputs. One, this is one, and another one is coming from QN bar, right? The QN bar comes and goes here. So this is QN bar. So 1 dot QN bar, right? Since this is a NAND gate, you get a whole bar, right? So this is nothing but the output will be QN, right? So what are you going to find? As I told you already, we are going to find QN plus 1. So QN plus 1 will be nothing but this QN. So you can simply write Qn plus 1 is nothing but Qn for the condition s equal to 0 and r equal to 0. Since you have found out a value for Qn plus 1, you need not worry about what is happening for 3 and 4, right? So you can go to the truth table and you can write this is Qn plus 1. That means for s equal to 0 and r equal to 0, whatever is there in the present state will be going to the next state, right? So there will not be any change about it. So we'll go with the next case study, next case. This is nothing but s equal to 0 and r equal to 1. Where am I taking these values? I'm taking these values from this truth table, right? So we can apply the same here and you can find out what is happening in this SR flip-flop. We have in the truth table S is 0, right? And what is R? R is 1, right? Now you can see in the first case you have already found out for S equal to 0, what is Qn? Qn plus 1. Qn plus 1 is nothing but Qn, right? The second case we have an S equal to 0, similar to the first case, right? Then what will be Qn plus 1? Qn plus 1 will be equal to Qn, right? Now in the second case we have R equal to 1, right? So we have to consider that also. Now you can see if both of them are 0 in the first case, S is 0, R is 0, there will be a Qn, you have this value, then this value is right. But you can see S equal to 0 and R is equal to 1, right? And you will not satisfy, you will not come to a conclusion that Qn plus 1 is equal to Qn. There is one more value that should be there because R is excited, R is equal to 1. Let's see how we can solve this. Before that, please understand, if you cannot come to a conclusion for Qn plus 1, you have to go for the complementary. That means Qn plus 1 bar, right? If you can find a value for Qn plus 1 bar, then you can automatically find a value for Qn plus 1 as well. Now we are going to find a value for Qn plus 1 bar, right? What is Qn plus 1 bar? That is what we are going to find. Now you can see this R is equal to 1 and the clock is also equal to 1. So R is 1 and the clock is also equal to 1 whole bar, right? 1 bar, 1.1 bar is 0, right? And this 0 is fed as an input to the NAND gate number 4 here, right? Also this is a 2 input NAND gate, right? 4 is a 2 input NAND gate. So one input is 0 and the other input is the output of NAND gate number 2, which is nothing but Qn. The Qn is coming and it is coming here and joining with 4. So 0 dot Qn whole bar, because this is a NAND gate, right? So what is 0 bar? 0 bar is nothing but 1. What is the output for NAND gate number 4? 1. What is the value for Qn plus 1 whole bar? It is 1. So Qn plus 1 whole bar is now 1. If Qn plus 1 bar is 1, what is Qn plus 1? It has to be 0, right? If A is equal to 1, what is A bar? A bar is equal to 0, right? What if A equal to 0, what is A bar? A bar should be equal to 1, right? The rules of the complements, right? You can apply the rules of the complements and you can find a value for Qn plus 1, right? So Qn plus 1, if S equal to 0 and R equal to 1 will be 0, right? Whatever may be the present state, whatever is there in the memory, right? If S is 0 and R is 1, it will be reset and it will be 0, right? So we'll move on to the next case. Next case will be equally interesting, right? So next case is nothing but, what is the next case in the truth table? S equal to 1, and see, you can find it. I'll just scroll back. This is the next state, S equal to 1 and R equal to 0. Let's see what happens to this. So we'll divide this screen. We'll put a line so that you can be comfortable in seeing, right? So S equal to 1 and R equal to 0, that is according to the truth table which is drawn here, right? So I'll just erase this and just come back to you. So this is the case 3. I'll just adjust the screen. This is the case 3, S equal to 0 and R equal to 1, that you know. So S is 1, R is equal to 0. So I have erased everything so that you can understand clearly. So the S is now excited, right? So in the previous case you can see S is 0, right? And the second case also S is 0, right? Now in the third case S equal to 1, we have turned on S. So S is set at high voltage. High voltage is nothing but plus 5 volts. Now this NAND gate 1 will be getting an input here. This is 1 from the S, this is 1 from the clock. So whole bar, which is equal to 1 bar. 1 bar is nothing but 0, right? So you can input this 0 when the low voltage to this NAND gate number 2. This NAND gate number 2 will also get an input from Qn bar, right? This is Qn bar, right? So how do you calculate this? So 0 from NAND gate number 1 and also Qn bar from NAND gate number 4, whole bar, right? So anything dot 0 is 0, right? And 0 bar is nothing but 0 bar, which is equal to 1. And this 1 will be the output for NAND gate number 2. And what is Qn plus 1? Qn plus 1 is also equal to, Qn plus 1 is also equal to 1, right? Since you have found out a value for Qn plus 1, you can put it on the truth table, 1. So this means if S equal to 1 and R is equal to 0, then whatever may be in the present state, right, this next state will be high, next state will be 1, right? So that means this 0 will be reset state, reset state, and this will be set state. Since S is excited, you call it set state, and if R is excited, you call it reset state, right? And there is a last case, right? We are going to see what is going to happen if both S and R both are excited. Let's see. If R is S equal to 1 and R is also equal to 1, what will happen? See, if both are excited, let's see, let's take it from the case study, case number 2. What is case number 2? Qn plus 1, right, is 0. Why especially case number 2? Because you can see in the case number 2, R is equal to 1, right? In the case 4 also, R is equal to 1. So in this case, you can see Qn plus 1 is equal to 0, right? In the previous case, you see S equal to 1, and in this case also S equal to 1. So Qn plus 1 in according to this case study number 3. I'll just put it here. This is from case study number 2, and this is from case number 3, right? So both these cases, they combine in case number 4. So in this case number 4, you are exciting S and R. S equal to 1 and R is also equal to 1. So you cannot find the value for Qn. Qn will be 0 and Qn plus 1, Qn plus 1 will be 0, Qn plus 1 will be 1. It will be 0 and 1, 0 and 1. So this case, you cannot use here, unused case or undefined case, UD case, undefined. You cannot use this case, right? So a device cannot be set and a device cannot be reset at the same time, right? So if you are using a smartphone and it hangs, you are going to reset your smartphone. Sometimes your laptop, sometimes your gadgets, right? They freeze, sometimes they hang. So we will reset them, right? So we will boot up the OS, right? If there is a bug or if there is a problem with the RAM, we will clear all the RAM, unwanted memory. You can free up the space in the RAM so that the device can boot up, right? So we used to do that. So a device cannot be set and reset at the same time. Either you can set it or you can reset it. Either you can use your phone or you can restart your phone. You cannot do this same process at the same time simultaneously. So the last part here cannot be used, it is unused, right? So this is how a set reset flip-flop works. All you have to do is to understand how a NAND gate works, right? And the latching between 2 and 4, and I'll try to draw a truth table like this, right? And you can put up the values for values for S and R, put zeros and ones and see how this communicates, right? So in every case you have to find the value for Qn plus 1, right? If you cannot get the value for Qn plus 1, and you can sort help from Qn plus 1 whole bar here, right? It will help you to find the value for Qn plus 1, right? If you have any doubts or need any clarifications, you can put it in the comment section or you can text me through WhatsApp personally. I'll help you, right? In the next class, we will be studying about JK flip-flop, which is a bit more sophisticated compared to SR flip-flop. It is not the best, but a bit more sophisticated, right? That we will see in the next class. Thanks for watching.